Okay, so today we're going to do a simple Bayesian calculation. Nothing more than actually Bayes' rule in this case. We're not doing a lot of complicated distributions, or if they are, they're discrete distributions. We will ask some simple questions. So first of all, we'll have a look at the question by going over to the iPad. So here we've got a simple setup. So we've got a thing called haemophilia. So this is where your blood can't clot properly, and so you bleed a lot. And basically, it's on what we call the X chromosome. And it's a recessive disorder. So to get it, you need both or all of your X chromosomes to have this particular mutation. So we're going to assume that a woman has a haemophilic brother. Her father is normal and her mother is a carrier. And we're going to denote a random variable theta, which will be 1 if the woman is a carrier and 0 otherwise. And it follows from the genetic conditions, figure 1, which I'm about to draw for you, that the prior distribution, though, before we get any information, is that the probability she's a carrier is a half, and the probability she's not a carrier is a half. And I'll explain where that comes from in a second. So this woman has 2 sons, of which neither have haemophilia. Find the probability the woman is carrier. And then the next thing is, suppose the woman has a 3rd son. Given that the first 2 sons are not haemophiliacs, what's the probability the 3rd son is not a haemophiliac? So first of all, let's think about it. Let's think about her father. So we know he doesn't have it. So males are what we call an XY. So they only have one X chromosome. And obviously, if he doesn't show any signs, that must be a normal X chromosome. While the mother, we know that females will have 2 X's. And we know that she's a carrier. So one of them has the haemophiliac gene. Oh, sorry, that didn't work. Like that. And so we will denote that as a H. Well, with the sons, for them to be sons, they basically must have got the Y. Sorry, no, we're talking about her. For her, because she's female, she must have got the X from the father. So the father just gives her the X. So the mother can give her one of these 2 genes. She should give the X or the XH. So there's 2 possibilities. One, she gets the X from the father and the X from the mother. And so in this case, she's not a carrier. The other possibility is that she gets an X from the father and the XH from her mother. In this case, she's a carrier, which is where we got that prior distribution for her. Okay, so let's think about the scenarios. First of all, let's consider the case that she's not a carrier. So in that case, the probability that S equals 0, so we're going to say S is the number of sons who are haemophiliacs, the probability that none of them are haemophiliac, the first 2, given theta equals 0, is equal to 1. Because she can't pass on a haemophiliac gene, so they're not going to be haemophiliac. So absolutely. If she's a carrier, so the probability that S equals 0, given theta equals 1, is going to be a half times a half, which is a quarter. Well, let's think about that. If she's a carrier, she looks like this. Ignore that, that should be my H. It's my bad handwriting. So in this case, she can either pass the X or the XH. So the probability that the first son is not haemophiliac, she must have passed the H. She chooses them independent equal probabilities, so that's a half. And the second one, the same, it's a half, so it's a quarter. So let's put that together. The probability that theta equals 1 given S equals 0 is going to be, well, we use Bayes' rule. It's the probability that S equals 0 given theta equals 1, the probability that theta equals 1 over, well, first of all, we have the same thing again. The probability that S equals 0 given theta equals 1, the probability that theta equals 1, plus the other possibility is the probability that S equals 0 given theta equals 0, the probability that theta equals 0. Running out of space there, which is a quarter times a half over a quarter times a half plus 1 times a half. That's all from above, which equals a fifth. Cool. So, what about the next question? Well, we'll denote the third son as S0. So we want the probability that S0 equals 1, that they have haemophilia, given the first two sons S equals 0. Well, that's going to be, we're going to have to go over all the possibilities for the mother. The probability that S0 equals 1, given theta, the probability of theta given S equals 0. So the first possibility is the probability that S0 equals 1, which is the third son that has haemophilia, given that she's a carrier, times the probability that she is a carrier, given S equals 0, plus the other probability is the probability that S0 equals 1, given that she is not a carrier, times the probability that she is not a carrier, given she has the first two sons are not haemophiliac. Well, first of all, that's a half. If she's a carrier, she's got a 50% chance she passes that XH on, times, well, we calculate the probability that she's a carrier as a fifth, plus. Well, if she's not a carrier, the third son can't get haemophilia, so that's 0. What's the probability that she is not a carrier? Well, if the probability she's a carrier is a fifth, the probability she's not a carrier is 4/5, which basically is a 10th. Cool. There's always a point in any calculations where I'm like, how can I test it? You know, if I'm writing code, I will go, how do I know my code's right? Let's do what I call a back of the envelope calculation, which is what we've just done. If I've done a calculation, I want to check it, then I will go and code it. And the idea is that both things match, then hopefully I haven't made a mistake. So I'm going to do that. I've got some code here now that we're going to go to. And what I've done is we're going to use some very simple simulations. So here I set up the father. The father is X and Y. And the mother of this woman is X and XH. And what I'm going to do is I'm going to simulate her. So I'm going to simulate the woman. So I take the father, the mother, the number of simulations, and that she's a woman. So basically, I randomly sample, and then the next thing I have to do is I have to say, well, she's only a woman if the father's gene was an X, because she has to be an X and an X. So we do that, and we do the counts. And we roughly get that the fact is that she's a haemophiliac happens 226 out of the total, so about the 50% that we did. Now what I'm going to do is I'm going to take each of the possibilities. So here's the possibilities. So in the first simulation, it's an X and X, and the second X and Y. So each of these, I'm going to use that to then simulate her sons. So in this function, I simulate her sons. So what we see here is this is the father's gene, the mother's gene, and this is what the sons have. So in this case, all the sons don't have haemophilia. In this one, she was a carrier, and so the second son had haemophilia. So the first thing we'll do is to say, well, let's calculate all the times where the first son and second son are not haemophiliac, so they're both X's, and then we count what the mother's gene looks like. And we can see here we've got, she's a carrier, so she has XH approximately 20% of the time, and she's not the rest of the time. So that agrees with my calculations roughly. The next one is we'll calculate the son is both X's, and we will look at the third one. And here we roughly get that the third one has haemophilia about a 10th of the time. So you are a nice little calculation just to illustrate how we can do some of these Bayesian calculations. Backed up by some code, and I highly recommend you, if you do some code and you want to know if it's right, go to a piece of paper, do the calculation, check they match. If you do a calculation or derivation and you want to check it's right, go to the code and do it there and check they match. It's a lovely way to check you're working and making sure it's working. Okay, that's everything. See you next time.